Okay, so in this section, we will learn a stoichiometry of thermochemical equations. Okay, so we know the stoichiometry. Stoichiometry is the ratios for the reactants and the products, or maybe between reactants or between products or between reactants and the products. So basically we have seen how we can correlate the molar ratios. So those are the stoichiometry. So a thermochemical equation is a balanced equation that includes delta H of the reaction. Delta H is the enthalpy that we had learned before. Okay. So in a thermochemical equation, you have a balanced reaction equation plus the delta H of the reaction. The sign of delta H could be positive or negative. It can tell us whether the reaction is exothermic or endothermic. Okay, remember for the exothermic reaction delta H is negative, and for endothermic reaction delta H is positive. And then the magnitude of the delta H, how big it is, will tell us O is proportional to the amount of substance. The value of delta H can be used in a calculation in the same way as a mole ratio. So this summarizes the relationship between amount and the heat energy transfer. If you have amount moles of substance in A, we can use in the molar ratio from the balanced equation, we can relate mole of substance A to mole of substance B. Now similarly, if you know the delta H of the reaction, just like the molar ratio, we can also correlate the number of moles of substance A or B to the heat absorbed or released, which is going to be the delta H. Okay. Now let's look at that concept with this example. The major source of aluminum in the world is bauxite, mostly aluminum oxide. Its thermal decomposition can be written as, so the reaction is given aluminum oxide. You heat it, when you heat it, you get aluminum and oxygen. And for this reaction, delta H is given as 1676 kilojoules. And this amount of heat is being absorbed when 1 mole of aluminum oxide is being used up, because this is a balanced reaction, right? In this balanced equation, there are 2 aluminums in the right hand side, and then the 2 aluminums, sorry, there are 2 aluminums on the left side, 2 aluminums on the right side, and there are 3 oxygen on the left and 3 oxygen on the right. So this is balanced. So in this balanced equation, delta H 1676 kilojoule is being absorbed when 1 mole of aluminum oxide is reacting, when 2 moles of aluminum being formed, or 3/2 of oxygen is being generated. So that is the relationship. If aluminum is produced this way, how many grams of aluminum can form when this much kilojoule of heat is transferred? Okay, it's asking how many grams of aluminum can form when 1.000 into 10 to the power 3 means 1000 kilojoule of heat is transferred. But what we know is this much heat is transferred when 2 moles of aluminum is reacted. But now we want to find out how many grams of aluminum can form when 1000 kilojoule of heat is transferred. So we started with 1000 kilojoules, so 1.000 into 10 to the power 3 kilojoules. And then just like our conversions that we've been doing before, we use the ratio that is given to us from the balance equation, 1676 kilojoules being absorbed when 2 moles aluminum is formed. Now it's asking how many grams. Now this step gives us the number of moles of aluminum being formed when 1000 kilojoule um, heat is transferred. What we want is the grams, so you're going to convert moles to grams. 1 mole aluminum is the molar mass of aluminum, which is 20, I believe it's 26. Aluminum is 26.98. Yeah, so 26.98. I'll show you that also. So 26.98 grams aluminum. So kilojoule cancel, moles aluminum cancel. When you solve the numerical values, you will get the grams of aluminum. Okay, and detailed plan how to be done also given here. And then so this is the same thing I just did with you guys. The mass of aluminum, you start with 1.000 into 10 to the power 3 kilojoules. From the stoichiometry of the balanced equation, 1676 kilojoules absorbed when 2 moles of aluminum produced, and then converting moles to grams, 32.20 grams of aluminum. So we can use the heat absorbed or heat released in a thermochemical equation using the stoichiometry. Okay. So another concept that we are going to learn is called Hess's law. What does the Hess's law says? Hess's law states that the enthalpy change of an overall process is the sum of the enthalpy change of its individual steps. Let's say you have a reaction, but this reaction can be done with several small steps. And then if you add up the several steps delta H values, overall delta H we can find from that individual values. That is the Hess's law. Enthalpy change of an overall process is the sum of the enthalpy change of its individual steps. Okay, delta H for an overall reaction can be calculated if the delta H values for the individual steps are known. And how do we do that? So what are the steps and what is the procedure? So let's see what we need to know in order to do this addition. Calculating delta H for an overall process. First, we need to identify the target equation, meaning the step whose delta H is unknown. And then we also need to know the amount of each reactant and product. How many moles are there? Okay, amount of each reactant and product. And then the next step, manipulate each equation with known delta H values so that the target amount of each substance is on the correct side of the equation. So to get the final equation from several other steps, we want to make sure the reactants and the products should be in the correct sides. I'll show you with the example that we're going to do. Change the sign of delta H when you reverse an equation. Let's say you are given a reaction, a forward reaction, but when you add it up to get you the target equation, you need to reverse the reaction. It's perfectly fine for you to reverse the reaction, but the value of the delta H changes if you do reverse a reaction. Okay, if the forward reaction reaction is positive delta H, if you reverse it, it would become negative delta H. Okay, and then multiply amount, meaning number of moles, and delta H by the same factor. If you do decide to multiply an equation to get to the correct number of moles, you have to multiply the delta H also by the same factor. After you manipulate your equations, add the manipulated equations and their resulting delta H values to get the target equations and its delta H. All substances except those in the target equation must cancel. Now let's look at all these steps with this particular example. two pollutants that form in automobile exhaust are carbon monoxide and nitrogen monoxide. Environmental chemists must convert these pollutants to less harmful gases through the following: carbon monoxide plus nitrogen monoxide giving you carbon dioxide and half nitrogen. This equation is balanced. That is going to be our target equation. Okay, this is going to be our target reaction. Carbon monoxide plus nitrogen monoxide giving you carbon dioxide and nitrogen. It's balanced, so it's half nitrogen. We want to find out the delta H for this reaction. We are also given two equations, A and B. Given the following information, calculate the unknown delta H. Now our goal is to rearrange and manipulate equation A and B such a way that when you add the A and B, we should get the final target equation as this one. Now if you look at equation A, carbon monoxide is in the left side. Target equation also carbon monoxide left side. Target equation doesn't have oxygen, but we do have oxygen. This can be cancelled later on. And carbon dioxide is in the product side, carbon dioxide in the product side. So we do not need to reverse this reaction. We can keep it like that. Also, it has the same number of moles, one carbon monoxide, one carbon dioxide. In your target reaction also, one carbon monoxide, one carbon dioxide. Let's look at equation B. Equation B, reactant side we have nitrogen, and then the product side we have nitrogen monoxide. Now we're going to look at in our target reaction, where is the nitrogen? It's right here, it's a product. And nitrogen monoxide here is a reactant. So equation B, we need to reverse equation B because we are going to add A and B to get the target reaction. So nitrogen monoxide is a product here and nitrogen monoxide is a reactant here. So we're going to reverse equation B. Okay. Plan. We know the amount of each substance and on which side each appears in the target equation. We adjust equations A and O, B and their delta H values as needed and add them together to obtain the target equation and to calculate the delta H. So we're going to reverse equation B. When you do reverse equation B, what's going to happen to the delta H? Delta H is positive 180.6 kilojoules. It's going to now, if you reverse it, delta H would become negative. Okay. And not only that, another thing that you need to do, we have to look up the molar ratio. So the molar ratio here, nitrogen is 1 mole right there. Here you have half nitrogen. And then here you have 2 nitrogen monoxide, but we only need 1 in the target reaction. So because of that, equation B also need to divide by 2. Okay, so when you do divide it by 2, then this would become half, this would become half, and this would also become 1. And if you divide the equation by 2, you also need to divide enthalpy also by 2. So it need to be reversed and also need to be divided by 2. Solution. Divide by 2 is similar to multiply by half. Multiply equation B by half and reverse it. So when you multiply by half and you reverse it, the product NO will become reactant NO. And then nitrogen, 1 nitrogen will become half nitrogen. Oxygen will become half oxygen. So the delta H, when you divide it by 2, it would become 90.3 kilojoules. Since we reverse it, it will become negative 90.3. Now we have a manipulated equation which is coming from equation B, and then we have equation A. Now add the manipulated equations together. Equation A going to stay the same. Equation B is now we divide by half. We have that equation 2. Now what we're going to do is we're going to add these two together. And their corresponding delta H values also written. Now we add these two together. Carbon monoxide going to be in the left side. Nitrogen monoxide on the left side. Half oxygen on the left side, half oxygen on the right side. So the same amounts of the same reagent get cancelled. And then the right side you have carbon dioxide. Right side you have half nitrogen, half nitrogen. Now when you add the delta H values for these steps, equation A and B, we can get the delta H for the reaction. So what we did from the given two reactions, we manipulated them such a way when they add together, we will get the target equation, which is what we want. And then similarly, we use the enthalpy values. You add these two enthalpies to find out the delta H of the target reaction. Okay, negative 283.0 plus negative 90.3 gives you delta H for the reaction negative 373.3 kilojoules. So that is the Hess's law. So the overall reaction delta H can be found by adding up other reactions. That gives you the overall reaction. So in this case, by adding 2 delta H values. Sometimes it could be 3 reactions gives you a final target equation, or maybe 4, something like that. Okay. So that is the example of